There are many examples of E1 reactions in which the skeleton of the alkene products does not seem to match that of the starter material, and we will now describe an acid-catalyzed dehydration of a secondary alcohol through the E1 mechanism, but with rearrangement of the carbocation skeleton to give these different products. The stepwise mechanism again begins with protonation of the alcohol to produce the alkoxonium species. The water-leaving group then breaks off, in this case to produce a secondary cation. And if the secondary cation undergoes intermolecular deprotonation, we get the minor product without rearrangement. However, since the secondary cation could be better as a tertiary cation, we see that a fast intramolecular rearrangement occurs in which one of the alkyl groups moves from the tertiary carbon to the secondary carbon, and this produces a tertiary carbocation. If this tertiary carbocation then loses a proton from the left, we produce the minor alkene as shown in 33%, and if we lose the proton from the right, we get the major product, which is formed in 64%. And so here we see the products of rearrangement to give a better carbocation, which then gives the alkene products based on Zaitsev's rule. Since we are at low pH, the first step will again be a fast protonation of the alcohol by the acid to produce the activated alkoxonium species. The water-leaving group will break off in the rate-determining step to form a secondary carbocation. And in a minor process, the secondary carbocation will be deprotonated to form the alkene shown in 3% yield. Most of the carbocations will undergo an intramolecular process as shown here, in which an alkyl group migrates to the secondary carbon in a fast intramolecular process to produce a more stable tertiary carbocation. The tertiary carbocation then has two types of beta hydrogen, which can be lost to form alkenes. In the first process we see here loss from the left to produce the less stable alkene in 33% yield. Loss of the beta proton on the right produces the tetrasubstituted alkene, which is therefore the major product. The E1 elimination process is therefore seen to be prone to rearrangement processes, in which an unstable secondary cation may rearrange to a tertiary cation to change the skeleton of the starter material and give products in which the backbone seems to be different. This example shows the secondary alcohol giving 3 different alkenes, 2 of which show the products of rearrangement. However, the outcome is still governed by Zaitsev's rule, in which the more highly substituted alkene is favored.